Something sits at the heart of every galaxy we have ever observed, a collapsed star with gravity so extreme that even light cannot escape. We have assumed for over a century that we know exactly what that thing is. We do not. What if the most feared object in the cosmos has a physical surface, a dark energy core, and zero entropy, and every instrument humanity has built cannot tell the difference? We are going to trace how these monsters form, watch the mathematics collapse at the point of no return, and follow two physicists who quietly proposed an alternative that changes everything. Like and subscribe if this journey grips you. Now, prepare yourself. We begin. The image has been burned into human consciousness for decades. A ring of white-hot fire curving around a perfect, absolute darkness. Light bending, twisting, swallowing itself at the edge. Nothing coming out. At the center, the void. You have seen it on magazine covers, in documentary thumbnails, on the walls of science classrooms. You think you know what it is. A black hole. The universe's most famous monster. Here is what most people carry as their understanding of the thing. It is a collapsed star, so massive and so dense that its gravity becomes unstoppable. It swallows matter. It swallows radiation. It swallows light itself, which is why the center appears completely black. At the heart of nearly every galaxy, including our own, sits one of these objects. The largest ones contain the mass of billions of stars, compressed into a region of space smaller than our solar system. The one at the center of the galaxy, M87, holds 6.5 billion times the mass of our star. The one anchoring the center of our own Milky Way holds roughly 4 million times that mass. The science says they are real. We have measured their gravitational influence on surrounding stars for decades. We have detected the ripples in space-time they produce when they collide. In 2019, a global network of radio telescopes produced the first actual image of one. The physics of black holes fills thousands of peer-reviewed papers. They are the best-studied exotic objects in all of astrophysics, and yet, somewhere underneath the familiar picture, buried inside the mathematics that describes these objects, there is a problem. Actually, there are several problems. They are not minor technical irritations waiting to be cleaned up with better instruments or smarter algorithms. They are fundamental contradictions embedded in the very definition of what a black hole is supposed to be. The picture you carry in your head of a black hole, the one that feels settled and confirmed, is built on a foundation that some of the most rigorous physicists alive believe is cracked. One physicist described it as carrying a broken engine in your best car and pretending the car still runs because the outside looks perfect. Here is the first crack, and we will return to it many times. At the center of every black hole, according to the mathematics of general relativity, the very theory that defines them, sits a singularity, a point where density becomes infinite, where the curvature of space-time becomes infinite, where the equations of physics stop producing meaningful numbers entirely. General relativity does not quietly fail here. It prints an error and shuts down. Physicists have known this for a century. They have largely agreed, quietly, that a singularity cannot be a real physical feature of the universe. Infinite density is not a physical prediction. It is a warning sign that the theory has exceeded its range of validity and needs help from another theory, one that does not yet fully exist. So the most famous, best studied, most confidently described object in astrophysics contains, at its core, something the theory itself cannot describe. That is the foundation. Now consider what gets built on top of it. Over the next several chapters, we are going to watch the black hole get constructed, layer by layer, until the cracks in the foundation become impossible to ignore. And then we are going to meet two physicists who decided to tear the structure down and build something completely different in its place. To understand why the crack matters, you have to understand how the monster forms in the first place. Let us go back to the beginning, not the beginning of the universe, but the beginning of the end for a very large star. Every star is a battle between two forces. Gravity wants to compress everything inward. The energy released by nuclear fusion pushes outward. For most of a star's life, these two forces hold each other in balance. And what you get is a stable, burning sphere that can last for millions or billions of years. Our star has been burning in this balance for nearly 5 billion years and will continue for roughly another 5 billion. But the fuel runs out. For a star with less than about 8 times the mass of our star, the ending is quiet by cosmic standards. The outer layers drift away and the core cools slowly into a white dwarf held up by quantum mechanical pressure between electrons. The story ends. For the heaviest stars, the story goes somewhere else entirely. When a star with many times the mass of our star exhausts its fuel, the outward pressure that kept gravity at bay simply vanishes. In less than a second, the core collapses. Instantly. In a fraction of a second, something that was roughly the size of our planet shrinks to a sphere about 12 miles across. Material crashes inward at roughly a quarter of the speed of light, piling up at the center until the density becomes so extreme that nuclear forces themselves push back. This creates a shock wave. The infalling outer layers slam into the rebounding core, and the result is one of the most violent events in the observable universe, a supernova explosion. It releases more energy in a few seconds than our star will radiate across its entire 10 billion year lifespan. What is left behind at the center depends on how massive the original star was. For stars in the medium-heavy range, the remnant core contains between 1 and 3 times the mass of our star, compressed into that 12-mile sphere. The quantum mechanical pressure between neutrons holds it up. This is a neutron star, already bizarre enough to deserve its own story. For the heaviest stars, the ones whose cores accumulate more than about 3 times the mass of our star after the explosion, neutron pressure is not enough. Gravity wins again. The collapse continues past even neutron star density, past any boundary that any known force can hold. And here is where we reach the question at the center of everything we are going to explore. What happens next? The standard answer, the one you will find in every textbook, is that the collapse continues without limit. The matter keeps compressing, the density keeps rising, and at some point the collapsing material crosses a threshold called the Schwarzschild radius, the critical size at which the escape velocity equals the speed of light. At that moment, according to classical general relativity, a black hole is born. But what actually happens in that final fraction of a second when everything crosses the threshold? The answer is stranger than most people realize. It starts at a very specific boundary in space-time, one that looks like nothing and means everything. Picture a river, smooth, wide, moving slowly toward the edge of a waterfall. Far from the falls, the current is gentle. You can swim against it easily, change direction, do as you like. The river barely constrains you. As you drift closer to the edge, the current picks up. Then you cross a certain line, a point that looks exactly like the rest of the river, and suddenly it is not possible anymore. The water is moving faster than you can swim. From this moment forward, there is only one direction. The falls are ahead of you. You are going over. That is the event horizon. The event horizon of a black hole is not a physical wall. It is not a barrier you can see or touch, not something marked in any way that would alert you as you crossed it. In fact, according to general relativity, crossing the event horizon of a sufficiently large black hole would feel like nothing unusual. No jolt, no alarm, no sensation of a boundary. What the event horizon actually is, precisely, is a location in space-time where escape velocity reaches the speed of light. Inside this boundary, the space-time geometry is curved so severely that every possible path, every trajectory, every direction of motion curves inward. There is no direction that leads back out. Even light, moving at the fastest possible speed in the universe, is swept inward with everything else. There are no exceptions. The radius at which this happens for a given mass was first calculated by Karl Schwarzschild in 1916, less than a year after Einstein published general relativity, and Schwarzschild did it while serving on the Russian front during the First World War. For our star, this critical radius would be about 2 miles. Compress our star down to a sphere 2 miles across, and nothing could escape from its surface. For a stellar mass black hole of about 10 times the mass of our star, the Schwarzschild radius is about 30 miles. For the supermassive object at the center of M87, it is roughly the size of our entire solar system. Once you cross the horizon, the future has only one destination: the center. The mathematics describes this with a kind of cold elegance. The radial coordinate inside the horizon behaves like time, always pointing inward, just as you cannot travel backward in time in your ordinary life. You cannot travel outward in space once you are inside a black hole. The geometry carries you forward, and forward means toward the center. This raises a question that took physicists decades to fully confront. What is at the center? If the horizon carries everything forward with no way back, and if the geometry inside the horizon drives everything toward a single point at the middle, then what waits at that point? General relativity has an answer. It is a very clean, very precise answer. It is also deeply troubling, and the closer you look at it, the more it begins to look less like a discovery and more like a confession. The theory is admitting, in the only language it has, that something has gone badly wrong. Let us follow the mathematics to its conclusion. Inside the event horizon, the collapse of matter does not stop. The infalling material keeps moving inward because the geometry leaves it no choice. As it moves inward, it compresses. As it compresses, the density rises. As the density rises, the curvature of space-time intensifies. And according to general relativity, this process has no natural stopping point. It continues until the matter is compressed into a region of zero volume and infinite density. This is the singularity. The word sounds dramatic, but the reality is stranger than the drama. A singularity is a place where the equations of general relativity return infinite values, infinite curvature, infinite density. The theory is not saying something very extreme happens here. The theory is saying the machinery has broken. The output is meaningless. Something outside this theory's descriptive range is occurring, and the theory itself cannot tell you what. Think of it as dividing by zero. You can set up the equation, write every symbol correctly, perform every step precisely, and then the last step produces a number that cannot exist. The mathematics has run off the edge of its own map. Any physicist will tell you privately that a singularity cannot be a real physical feature of the universe. Infinite density is not a prediction. It is a symptom, a red flag, a signal that you have pushed your equations outside the domain where they remain valid. When a physical calculation produces an infinite answer, the correct response is to recognize that the theory needs supplementing by another framework that handles the extreme regime more carefully. In the case of black hole singularities, the framework everyone is waiting for is quantum gravity, a complete theoretical structure that merges general relativity with quantum mechanics. The problem is that no complete theory of quantum gravity exists. Attempts have been made. Loop quantum gravity, string theory, various hybrid approaches, all have partial successes and partial failures. None is finished. So here is what we have right now, today. The equations of general relativity drive everything inside a black hole toward a singularity. The singularity is mathematically well defined. It is also physically absurd. Physicists have been carrying this absurdity in the very center of their best theory of gravity since 1916. For a long time, many physicists hoped the singularity was a quirk of the idealized solutions they were studying, not a genuine prediction. They hoped a more realistic, rotating, lumpy, collapsing star would avoid it. They hoped the problem would resolve itself once a more complete theory arrived. Then, in 1965, Roger Penrose removed the hope. What Penrose proved with complete mathematical rigor was that the singularity was not an artifact of idealization. It was a necessary consequence, provably unavoidable under the assumptions of general relativity, for any collapsing object that reached sufficient density. The hope was closed off. But Penrose's proof required certain assumptions, and one of those assumptions turns out to be the thread that, when pulled, unravels the entire black hole picture. That thread has a name. It involves the behavior of matter under extreme gravitational pressure, and it leads directly to something strange about the fabric of empty space. Roger Penrose was 34 years old when he proved that singularities were unavoidable, and the proof was elegant enough to eventually earn him the Nobel Prize in Physics in 2020. But the proof does not say what most people assume it says. Here is what it actually claims. If a region of space-time contains what is called a trapped surface, a closed surface from which light rays in all directions are converging inward rather than spreading outward, then a singularity must follow. The trapped surface is the critical concept. It forms when a collapsing object reaches sufficient compactness. Once it exists, the future of that region is predetermined by the mathematics. A singularity will develop. The proof is watertight given its assumptions. Penrose and Hawking together extended it in 1970 to cover cosmological cases as well, showing that the Big Bang itself contained a past singularity of this kind. The theorems became foundational. They convinced the physics community that singularities were not a bug in special solutions, but a generic feature of general relativity, showing up wherever gravity became strong enough. Here is where things get interesting. Every mathematical theorem is only as strong as its assumptions. The Penrose singularity theorems require, among other things, that matter obeys what are called the energy conditions. These are reasonable-sounding requirements that effectively say matter should have positive energy density and positive pressure, that it should not be exotic in a specific and mathematically precise way. For every form of matter ever encountered in a laboratory, these conditions hold comfortably. Rocks, gas, plasma, neutrons, compressed nuclear matter, all of them satisfy the energy conditions with room to spare. But the universe contains something else. Since the late 1990s, observations of distant supernovae confirmed that the expansion of the universe is accelerating. Galaxies are flying apart from each other faster and faster. Something is pushing them, overcoming gravity at the largest scales. That something is called dark energy, and it has a very specific mathematical signature. Its pressure is negative. Enormous, outward pushing, repulsive negative pressure. Dark energy violates the energy conditions that the Penrose theorems require. The implications are enormous. If the vacuum of space can carry genuine negative pressure, then matter under extreme conditions might be able to adopt a similar state. If that happens inside a collapsing star, the singularity theorems lose their grip. The loophole opens. The cracks in the foundation of our black hole picture keep widening. A singularity that cannot be physical, a mathematical proof that prevents us from escaping it, and now a known, observed, real component of the universe that violates the assumption the proof requires. But these are still theoretical worries. Physics has always been able to carry theoretical worries for a while and manage. What happened next is that the quantum properties of black holes turned a theoretical embarrassment into an outright contradiction that cannot be waved away. And the person who discovered it was the most famous physicist of the 20th century's second half. In 1974, Stephen Hawking applied quantum mechanics to the region just outside a black hole's event horizon and got an answer that changed everything. Black holes glow, not visibly. For any black hole we have ever detected, the radiation is so faint that it would be trillions of times colder than the cosmic microwave background, the afterglow of the Big Bang that fills all of space. We have no hope of measuring it directly with any existing instrument. But the principle is what matters. And the principle was devastating. Here is the mechanism. Quantum mechanics describes empty space as seething with virtual particle pairs, particles and antiparticles that flicker in and out of existence constantly, borrowing energy from the vacuum and paying it back so quickly that ordinary physics never notices. Under ordinary circumstances, these pairs annihilate each other and nothing remains. Near the event horizon of a black hole, something different can happen. A virtual pair appears right at the boundary. One of the pair falls inward past the horizon. The other, finding itself on the outer side, cannot instantly reunite with its partner for annihilation. It escapes. It becomes real. And the energy it carries has to come from somewhere. It comes from the black hole. Over vast timescales, this process slowly drains energy from the black hole, degree by infinitesimal degree. Given enough time, the black hole radiates away all of its mass and disappears entirely. This is Hawking radiation, and it immediately raised a problem that looked at first like a philosophical nuisance and turned out to be one of the deepest contradictions in modern physics. The radiation that escapes is thermal. It is featureless, structureless, random heat radiation carrying no information about what fell into the black hole. If you drop an entire library into a black hole and collect all the Hawking radiation it emits over its lifetime, quantum mechanics says that radiation cannot tell you anything about what was inside. The history is gone. But quantum mechanics also says, with equal firmness, that information cannot be destroyed. The complete state of a physical system must always evolve in a way that allows you, in principle, to trace it backward and recover the full history. This is called unitarity. It is not a guideline or a rule of thumb. It is a foundational requirement for quantum mechanics to be logically consistent. If Hawking radiation is truly thermal and black holes truly evaporate completely, then a black hole is a machine that takes in information and outputs nothing but randomness. The universe forgets, unitarity breaks. Both things cannot be true at once. Black holes cannot simultaneously obey the rules of general relativity and the rules of quantum mechanics. One of them has to be wrong, or the picture of what a black hole actually is has to change. This is the black hole information paradox. It was born in 1976. By 2026, it still has no universally accepted solution. And in 2012, it got significantly worse. By 2012, most physicists had quietly converged on a belief that information was probably preserved somehow during black hole evaporation, even if the exact mechanism remained unclear. The information was assumed to be encoded in subtle correlations within the Hawking radiation, hidden from easy view but technically still present. This was an uncomfortable position, but a livable one. Then 4 physicists published a paper that made it unlivable. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully showed that the comfortable assumption was not merely unclear, it was impossible. Their argument starts from 2 bedrock principles. The first is that information is preserved. Quantum mechanics demands it, and by 2012, most physicists were prepared to defend this. The second is the equivalence principle, Einstein's foundational insight that a person falling freely in a gravitational field cannot distinguish that experience from floating in empty space. The equivalence principle says that crossing an event horizon should feel like nothing special. A freely falling observer should experience smooth, ordinary space-time at the boundary. These 2 principles, both considered non-negotiable, turn out to contradict each other. For information to escape from an evaporating black hole, the Hawking radiation emitted late in the black hole's life must be entangled with the radiation emitted early. This is the only way to build up the correlations that would allow information to be recovered. But quantum mechanics also says a particle can only be maximally entangled with one other system at a time. The late-stage radiation cannot simultaneously be entangled with early radiation and with particles inside the horizon. If it is entangled only with early radiation, the particles just inside the horizon are stripped of their expected entanglement with the interior. A region of broken entanglement at the horizon translates, through quantum mechanics, into high energy, a wall of radiation at the boundary, a firewall. Any observer crossing the horizon, expecting smooth freefall as Einstein's equivalence principle promises, would instead be instantly incinerated. This creates an irresolvable trilemma. You can have at most two of the following three things: information preservation, smooth horizon crossing, or standard quantum field theory at low energies. All three are foundational to modern physics. All three are supported by evidence in countless other contexts. All three cannot survive the interior of a black hole together. Here is the suspicion that began to crystallize among a subset of theorists. If every paradox we encounter, the singularity, the information loss, and now the firewall, is rooted in the existence of the event horizon, then perhaps the right answer is to ask whether the event horizon actually exists at all. Eliminating the horizon requires replacing the black hole with a different physical object, something that looks identical from the outside but has completely different interior physics. Before we meet that object, there is one more broken piece of modern physics to examine. A prediction so catastrophically wrong it is almost hard to take seriously, and a connection to cosmological physics that is about to make an unexpected appearance inside a dying star. Here is a calculation that every physicist knows about and almost nobody discusses in public. Quantum field theory, the most precisely tested physical theory in human history, describes the fabric of empty space as a seething foam of virtual particles. Pairs of particles flickering into existence, borrowing energy from the vacuum for tiny fractions of a second before annihilating again. This process gives the vacuum an energy density, a baseline level of energy that empty space carries simply by virtue of existing. You can calculate this energy density. The mathematics is standard and uncontroversial. When you do the calculation, you get a number. The problem is what happens when you compare that number to the actual energy density of empty space measured from observations of the universe. The two numbers are not slightly different. They are not off by a factor of 10 or 100 or even 1,000,000. The theoretical prediction and the measured value differ by a factor of somewhere between 10 to the 60th power and 10 to the 120th power, depending on exactly how you perform the calculation. To give you a rough sense of what that means, the number of atoms in the entire observable universe is roughly 10 to the 80. The disagreement between quantum field theory's prediction and reality exceeds even that. Some versions produce a discrepancy larger than the total count of possible quantum states in the entire observable universe. This is called the cosmological constant problem. It is widely considered the most catastrophic mismatch between theory and observation in the history of science. It has no accepted solution. Menon Day, and for the purposes of our story, it tells us something crucial. Quantum field theory predicts that the vacuum is capable of carrying an enormous energy density. The observed value is tiny, but the theoretical machinery that generates large vacuum energies is well established and not disputed. Now consider what happens when a massive star collapses and the density of matter in its core rises toward extreme values. As the curvature of space-time intensifies, as the matter density climbs to values trillions of times denser than an atomic nucleus, the quantum vacuum surrounding and permeating the collapsing material is being squeezed and subjected to gravitational conditions that exist nowhere else in the observable universe. Under these conditions, quantum field theory predicts that the vacuum can undergo a phase transition. A phase transition is when a system abruptly changes state as conditions change. Water does not become ice slowly and continuously. It reaches a critical temperature and snaps into a new crystalline state with completely different properties. The quantum vacuum, under extreme gravitational compression, could do something analogous. It could snap into a new state, one with very different properties than the vacuum you and I inhabit. In particular, a vacuum phase transition under extreme gravitational conditions might produce a state with negative pressure, a state where the energy of the vacuum pushes outward rather than surrendering to gravity, a state that resists collapse rather than being crushed by it. This is where the cosmological constant problem stops being an embarrassment about astronomical measurements and becomes directly relevant to the physics of a dying star. The same mathematical structure that makes quantum field theory predict catastrophically wrong values for the vacuum energy in flat space also predicts that the vacuum can carry enormous amounts of energy under the right conditions, with exactly the kind of negative pressure that would halt gravitational collapse. Two physicists noticed this connection. In the autumn of 2001, they uploaded a paper to a public server. Nobody paid much attention at first. That oversight turned out to be significant. In September of 2001, a researcher at the University of South Carolina and a researcher at Los Alamos National Laboratory quietly posted a proposal to a public physics archive. The first was Powell Mazur. The second was Emil Motola. Their paper attracted little attention in the immediate aftermath. 3 years later, a refined version appeared in a major science journal. The idea inside was radical enough that it took the community years to fully reckon with it. The title was precise and technical: Gravitational Condensate Stars, an alternative to black holes. Inside, Mazur and Motola were not claiming to have found a mathematical error in general relativity. They were not disputing the Penrose singularity theorems or the derivation of Hawking radiation. They accepted all of it. What they claimed was that the established physics was incomplete in a specific and important way. It did not properly account for what happens to the quantum vacuum when space-time curvature approaches the critical value that would normally create an event horizon. Their argument ran as follows. As a massive star collapses and its radius shrinks toward the Schwarzschild limit, the gravitational field at the boundary reaches an intensity unlike anything in ordinary astrophysics. The gravitational redshift at that boundary diverges toward infinity. And under these extreme conditions, the quantum vacuum does not simply continue being what it was in flat space. It undergoes a phase transition analogous in a precise mathematical sense to Bose-Einstein condensation. Bose-Einstein condensation is a quantum effect observed in laboratory settings with ultra-cold atoms. When certain particles are cooled to extreme temperatures, they abruptly lose their individual identities and collapse into a single, shared quantum ground state. The ensemble stops behaving like a collection of separate particles and starts behaving like one giant coherent quantum object. The transition is sudden. The new state has completely different properties from the previous one. Mazur and Motola proposed that something analogous happens at the forming horizon of a collapsing star. The intense gravitational field, rather than simply intensifying without limit past the Schwarzschild boundary, triggers a phase transition in the quantum vacuum itself. The entire interior of the collapsing region snaps into a new quantum ground state, a gravitational condensate. The horizon, the mathematical boundary from which nothing can escape, never actually forms. What forms instead is something else entirely. They called it a gravitational vacuum condensate star. The name was soon shortened to Gravastar. The Gravastar contains no singularity. It contains no event horizon. It traps no information. It generates no firewall. Every paradox that required an event horizon to exist dissolves completely in this picture. The objection arrived immediately. If a gravastar has no event horizon and no singularity, what does it actually have? And how can it possibly be consistent with all the observations that seem to confirm black holes? The answers are in the architecture of the object itself. That architecture is three distinct layers, each with its own physics, each playing a precise role in holding the whole structure together. And the layer at the heart of a gravastar contains something that will sound deeply familiar. It is the same physics that operates at the scale of the entire universe. A gravastar is an object with three concentric regions, each governed by different physics, each serving a specific structural purpose. Understanding how it is built is the key to understanding everything that comes after. The outermost region is the simplest. From any distance greater than the gravastar's surface, the space-time surrounding a gravastar is identical to the space-time surrounding a black hole of the same mass. The mathematics describing it is the Schwarzschild geometry, the same solution to Einstein's field equations that describes the exterior of any spherically symmetric, massive object. Light bends around it in the same way. Stars orbit it in the same way. The gravitational pull at any given distance is identical. Everything that astronomy has ever used to detect, measure, or observe a black hole candidate would produce the same results around a gravastar of equal mass. From the outside, the two objects are indistinguishable. Then you reach the surface. A black hole has no surface. Its outer boundary is an event horizon, a mathematical concept, a location in spacetime defined entirely by the behavior of light rays. There is no material there, no texture, no substance, passing through it. If classical general relativity is correct, would feel like absolutely nothing. A gravastar has a physical surface. It is a thin shell of real material, sitting precisely at the radius that would otherwise be the Schwarzschild radius. This shell is not made of ordinary matter. It is composed of ultra-stiff material with an equation of state that places it at the maximum stiffness permitted by the theory of relativity. The shell has real tension, real energy density, real substance. Anything approaching the gravastar from outside would eventually encounter this boundary. The existence of this shell resolves, by physical fact rather than theoretical argument, every paradox associated with the event horizon. There is no horizon to produce firewalls. There is no one-way boundary to trap information forever. There is a physical wall. And physical walls have physics. Inside the shell, everything changes. The interior of a gravastar is filled with a quantum vacuum in a new phase of matter. And this new phase has a specific mathematical description. Its pressure is equal to its negative energy density. Written as an equation, pressure equals negative rho. You have encountered this equation already in this story. It is the equation of state for dark energy, the same invisible, pervasive component of the universe that is causing the expansion of the cosmos to accelerate. The same physics thought to be responsible for the inflationary expansion of the universe in its earliest moments. Inside a gravastar, the physics driving the expansion of the entire universe is the physics of the interior. The dark energy core pushes outward. The shell holds the line. The gravitational field of the whole structure holds it together from outside. The three layers balance each other in a stable equilibrium. The mathematics is rigorous. The equations that generate black holes as predictions of general relativity generate gravastars as well. In the original formulation, Mazur and Motteler showed that the junction between the dark energy interior and the Schwarzschild exterior can be made exactly smooth using well-established mathematical machinery, and a subsequent analysis in 2004 confirmed the structure is stable. Both objects are valid, exact solutions to Einstein's field equations. What exactly is the dark energy interior in physical terms, though? What does a region of negative pressure actually mean for anything that enters it, or for the nature of the object as a whole? That question leads somewhere that will change how you think about the things sitting at the heart of every galaxy in the sky. The interior of a gravastar carries a physics so extreme that comparing it to anything in every day Experience requires a concept almost no one encounters in ordinary life. But you have already heard the name. Several chapters back, when we traced the crumbling logic of the singularity theorems, we arrived at a known, observed, real component of the universe that violated the energy conditions those theorems require. We called it dark energy. The same physics that is pushing galaxies apart right now, accelerating the expansion of the entire cosmos, lives inside the core of every gravastar. That is not a metaphor. It is the precise mathematical claim. The equation that describes dark energy is written simply. Pressure equals negative energy density. When physicists express it symbolically, they write P equals negative rho. That minus sign is doing the most important work. It means the energy density of this substance pushes outward, repulsively, against gravity rather than adding to the inward pull. Every other known form of matter adds weight. This subtracts it. Press it from the outside, and it pushes back harder. Inside a collapsing star, as the density climbs toward the threshold that would normally produce an event horizon, Mazur and Matola's proposal is that the quantum vacuum adopts precisely this equation of state. The pressure flips sign. The collapse encounters an outward force that scales with the very density trying to crush it. The harder gravity squeezes, the harder the interior pushes back. The collapse halts. The singularity never forms. The geometry that results from filling a region of space with this kind of energy is called de Sitter spacetime, named after the Dutch astronomer Willem de Sitter, who derived the solution in 1917. De Sitter spacetime describes a region dominated entirely by a positive cosmological constant, by repulsive vacuum energy. It has a specific geometric structure that appears in two other contexts in modern cosmology. The inflationary period immediately after the Big Bang, when the universe expanded by an enormous factor in a tiny fraction of a second, and the far future of our universe, which observations suggest, will eventually settle into an eternally expanding de Sitter state. A gravastar contains, inside a sphere smaller than our solar system, the same geometry that governed the birth of everything and will govern the eventual fate of everything. The interior de Sitter spacetime has a horizon of its own, a de Sitter horizon, marking the boundary of the interior region. In the Mazur-Motolar construction, this interior de Sitter horizon sits at exactly the same radius as the Schwarzschild radius of the outer geometry. The two horizons, one from the outside in and one from the inside out, sit back to back at the same location. Between them stands the shell. What this means physically is that the dark energy core is a self-contained patch of repulsive spacetime, bounded by the shell, generating outward pressure that exactly balances the inward pull of the gravastar's own gravity. Without the shell to contain it, the interior would expand. Without the dark energy to resist, the shell would collapse. The equilibrium is precise. Here is where the architecture begins to feel as though it was designed rather than discovered. The same component of the cosmos responsible for the largest scale structure of the universe, the component that is pulling galaxies apart across billions of light years, is the component that holds together the smallest scale collapse structure, the remnant of a dead star. That balance requires a physical surface that can withstand both pressures simultaneously. And the material that surface is made of has properties unlike anything in a physics textbook. Everything we know about the event horizon of a black hole tells us it is the most consequential boundary in the universe. It divides regions of space-time from each other permanently. Matter crosses it and does not return. Light crosses it and does not return. Information crosses it and, according to the paradox we traced in earlier chapters, may not return either. For over a century, the event horizon has been defined, in part, by what it lacks. There is no substance at that boundary, no wall, no material, no physical presence, only geometry. A gravastar replaces that boundary with something that actually exists. The thin shell of a gravastar sits at the same radius that would otherwise be the event horizon. Unlike the event horizon, it is made of matter, real matter, with real physical properties, subject to real physical laws. Anything falling toward a gravastar from outside would eventually reach this surface and interact with it, the same way you interact with a wall by running into it. The philosophical mystery of the event horizon, the one-way boundary you cannot detect as you cross it, simply does not appear here. The material composing the shell has a specific equation of state. Pressure equals positive energy density. This is called ultra-relativistic stiff matter. It represents the maximum stiffness that matter is allowed to have under general relativity. If you tried to compress it further, the speed of sound inside it would equal the speed of light. The upper limit relativity permits. It is, in a precise theoretical sense, the hardest material general relativity allows. Think of the shell as performing 3 jobs simultaneously. It must hold back the outward pressure of the dark energy core trying to expand. It must resist the inward pull of the gravastar's own gravitational field. And it must do both of these things at a radius barely larger than the Schwarzschild radius of the whole structure. The shell exists in an extraordinarily tight mechanical balance. The mathematical machinery that ensures this balance works was developed by the Canadian physicist Werner Israel in 1966. His junction conditions specify precisely what properties a thin surface must have to join 2 different spacetime geometries without producing a contradiction. For the gravastar, these conditions calculate the exact surface energy density and surface tension the shell must carry to smoothly stitch the de Sitter interior to the Schwarzschild exterior. The junction conditions are a standard tool of general relativity applied here to a specific and mathematically well-defined problem. The gravastar solution satisfies them exactly. The geometry on both sides of the shell joins cleanly. There are no discontinuities, no gaps, no mathematical crimes being committed at the boundary. There is something worth sitting with in this picture. The event horizon of a black hole is philosophically troubling precisely because it has no physics. It is a consequence of geometry, a location in space-time that behaves differently from all other locations while looking and feeling identical to them. The paradoxes we traced through the previous chapters, the information problem, the firewall, all arise from the fact that this invisible, undetectable boundary separates regions of physics with completely incompatible rules. The gravastar's shell has physics. It has tension, energy, and material properties. When something falls in and hits it, physical processes occur at the boundary. The universe does not need to choose between quantum mechanics and general relativity at this location because the location is no longer a one-way door. It is a wall. Walls have physics. What caused this wall to materialize during the collapse, rather than simply vanishing into a horizon, is the strangest part of the story, and it requires going to a scale that makes atomic physics look large. The most natural objection to the gravastar picture is also the most obvious one. If the mathematics of general relativity predicts that gravitational collapse produces a black hole, and if the Penrose singularity theorems prove that a singularity must follow, then how does a gravastar form at all? What interrupts the collapse before the horizon appears? The answer requires going somewhere most astrophysics discussions never go. Quantum mechanics in curved spacetime. Quantum mechanics at the scale of atoms and particles is familiar. Things exist in superpositions. Particles borrow energy from the vacuum for tiny instants. Systems are described by wave functions rather than definite positions. All of this happens at microscopic scales and, in ordinary circumstances, has no visible effect on the behavior of large objects. The curved spacetime near a forming horizon is not ordinary circumstances. As a massive star collapses and its radius approaches the Schwarzschild limit, the gravitational redshift at the boundary between interior and exterior grows without bound. In ordinary coordinates, the infalling material slows to a halt and the redshift diverges to infinity. The quantum vacuum at this boundary is subjected to a gravitational stress unlike any other environment in the universe. And quantum field theory in curved spacetime predicts that the vacuum responds. The mechanism identified by Emil Mottola is called the conformal anomaly, sometimes called the trace anomaly. It is a quantum effect, the breaking of a classical symmetry when quantum fields are placed in curved backgrounds. In most settings, this anomaly produces small corrections. Near a forming horizon, where the curvature is becoming extreme, it generates a large, coherent stress in the vacuum energy. That stress is not a perturbation. It triggers a phase transition. The analogy Mazur and Mottola drew explicitly is to Bose-Einstein condensation, the quantum process discovered in laboratory settings with ultra-cold atoms. A gas of particles cooled toward absolute zero reaches a critical temperature and stops behaving as individual particles. The entire ensemble collapses into a single shared quantum ground state. The system does not gradually change. It flips. One moment, you have a collection of separate particles. The next moment, you have a single macroscopic quantum object with collective properties no individual particle possesses. The proposal is that the quantum vacuum near the forming horizon undergoes an analogous flip. The gravitational field reaches a critical intensity. The vacuum, rather than continuing to exist in its ordinary flat space phase, snaps into a new phase, the gravitational condensate. The entire interior of the collapsing region transitions simultaneously into a coherent quantum ground state. In this new state, the interior carries the dark energy equation of state. The outward pressure appears. And crucially, the horizon never crosses the threshold to full formation. The boundary of the condensate freezes at the radius where the transition occurred, and the shell crystallizes at that location. The physics is quantum. The scale is stellar. The result is an object that general relativity alone cannot produce, but that quantum field theory in curved spacetime predicts is what actually happens. The idea remains unproven. Mottola's framework is a theoretical proposal, and the debate continues. The formation mechanism remained the most criticized gap in the Gravastar picture for over 2 decades, until a paper in September of 2025 presented the first dynamical model for how a gravastar could actually form during gravitational collapse. That was the first attempt to demonstrate the phase transition in realistic collapse conditions rather than idealized mathematics. The theory now has a story for how the gravastar comes to exist, but whether it would be detectable once it does brings us to the most unsettling feature of the whole scenario. Stand far enough from a gravastar, and you will never know it is not a black hole. The limitation runs deeper than any instrument or technology gap. It is a mathematical fact built into the structure of general relativity. The exterior spacetime of a gravastar is the Schwarzschild geometry, identical in every measurable property to the exterior of a black hole with the same mass. The gravitational acceleration at any given distance is the same. The deflection of passing light is the same. The orbital periods of stars and gas clouds circling it are the same. The gravitational redshift of any signal emitted near it is the same. Every method astronomers have used to confirm the existence of black holes over the past century, measuring the speeds of stars in galactic nuclei, tracking the orbits of objects around Sagittarius A times at the center of our own galaxy, detecting the light from accretion disks, recording gravitational waves from mergers. All of these methods probe the exterior spacetime geometry. All of them would return exactly the same answers for a gravastar as for a black hole. Every object we have ever confidently identified as a black hole might be a gravastar. Every image, every orbital measurement, every gravitational wave detection accumulated over decades of observation is consistent with both possibilities. We have no historical observation that distinguishes between them. Mazur and Mottola built this in deliberately. For a gravastar to be scientifically viable, it cannot violate the successful predictions of general relativity for the region outside a collapsed object. It must reproduce every observational success of the black hole picture. The exterior Schwarzschild geometry ensures this. The disguise is perfect by design. The result is philosophically vertiginous. Consider what it means for the image released by the Event Horizon Telescope in 2019, the iconic photograph of the glowing ring surrounding a dark central region at the heart of the galaxy M87. That image was hailed as the first direct visual confirmation of a black hole. The bright emission ring exists because the extreme gravity of the object creates a photon sphere, a region where light can orbit in circles. The dark central shadow is the region from which light cannot reach distant observers. A gravastar compact enough to lie within its own Schwarzschild radius also has a photon sphere at the same location. Light would orbit it in circles. A shadow would appear in the same place for the same geometric reason. The image produced by both objects would be qualitatively identical. The Event Horizon Telescope confirmed that something extremely massive and extremely compact sits at the center of M87. It did not confirm that an event horizon exists, because it cannot. Because the exterior geometry of both objects looks the same. The disguise holds for every existing instrument we have built, every detection we have made, every image we have captured. But the disguise is not perfect everywhere. There is one specific regime where the two objects behave differently, a regime that was not accessible to the instruments of the 20th century, barely accessible to the instruments of the 21st, and that the next generation of detectors is being explicitly designed to probe. The difference lives in the interior, and the only way to read what is inside is to listen to how the object rings. Inside a gravastar, the ordinary rules of black hole physics do not apply. There is no singularity waiting at the center. There is no one-way flow of space-time carrying everything inward. There is no point where the equations of general relativity stop producing meaningful answers. What the interior contains instead is something that physics can fully describe at every point. The space-time geometry inside a portal. Gravastar is de sitter, space-time, the same geometry that governs two other extraordinary settings in our universe. The first is the inflationary epoch of the very early universe, the phase immediately after the Big Bang when the cosmos expanded by a colossal factor in a tiny sliver of time, driven by the same kind of repulsive vacuum energy that fills the gravastar interior. The second is the far future of our universe, which the observed acceleration of cosmic expansion suggests will eventually become a perpetually growing de sitter state. De sitter space-time has properties that are the precise opposite of a black hole interior. A black hole interior is geodesically incomplete. This is the technical term for what happens at a singularity. Paths through space-time, the trajectories that particles and light follow, terminate abruptly at a finite point. They do not smoothly continue. They end, the way a road ends at a cliff edge. The theory has no description of what lies beyond. De sitter space-time is geodesically complete. Every path that enters it continues forward without interruption. No trajectory ends prematurely. Every point in the interior is connected to every other point by a valid path through space-time. The laws of physics hold at every location, under every condition, without exception. A black hole interior is a room where the floor progressively disappears as you walk across it. The closer you get to the center, the more of the floor is gone, until at the singularity there is nothing left to stand on. Physics cannot describe what is there, because the concept of standing there has lost meaning. The gravastar interior is a room where the floor holds all the way across. You can walk to the far wall. The far wall is the shell. Physics holds at every step. Here is the structural detail that makes this work mathematically. The de sitter interior has its own kind of horizon, called the de sitter horizon, marking the boundary of the region a stationary observer inside could access. For the gravastar, Mazur and Mottola showed that this de Sitter horizon sits at exactly the same radius as the Schwarzschild radius of the exterior geometry. The two boundaries coincide. The shell sits precisely at this shared radius. The alignment follows directly from the equation of state of the interior combined with the junction conditions that join the two geometries. The de Sitter radius of the interior is determined by the gravastar's mass, and it equals 2 times the gravitational constant times the mass. For any gravastar of any mass, the interior and exterior horizons always coincide at the shell. The implication is profound. A gravastar is a self-contained physical system where two radically different space-time geometries, representing the two vacuum states of the universe we actually live in, fit together like two hemispheres of a sphere. The outer Schwarzschild geometry is the vacuum state of our ordinary universe. The inner de Sitter geometry is the vacuum state of a universe dominated by dark energy. Every gravastar is a pocket universe enclosed within the remnant of a collapsed star. The deeper we go into the physics of this object, the stranger it becomes. The next layer down is stranger still, because it is not about geometry. It is about the quantum nature of the object as a whole. Most things in the universe behave either as classical objects or as quantum objects. Rocks are classical. Electrons are quantum. The line between them is approximately drawn at the scale of atoms. Below it, quantum effects dominate. Above it, classical physics takes over. The boundary holds so reliably in practice that almost no one spends time questioning it. The gravastar erases that line. Mazur and Mottola's deepest claim is that the interior of a gravastar is a macroscopic quantum condensate, a single coherent quantum object. An entity where the quantum nature of the vacuum is not a microscopic correction or a perturbative effect, but the defining property of the entire structure, which may contain the mass of millions of stars. The analogy is Bose-Einstein condensation, which we touched on when discussing the phase transition that forms a gravastar. But the implications of that analogy go further than the formation story. In a Bose-Einstein condensate, particles lose their individual identities. Millions of atoms cooled into the condensate no longer exist as separate quantum systems. They share a single wave function. The condensate is, quantum mechanically, one thing. It has properties that emerge only because of this collective unity, properties no individual atom possesses. Change one part of it, and the whole responds coherently. The concept of individual atoms inside a condensate has dissolved. The gravastar interior is the gravitational analog of this. The quantum vacuum inside the shell has condensed into a single shared ground state. The entire interior is one quantum object. Its equation of state, pressure equals negative energy density, is not a property of any individual component, but an emergent property of the condensate as a whole. There are no individual vacuum fluctuations inside the gravastar doing their own quantum business. There is one thing, behaving coherently. This is what Mazur and Mottola meant when they called the structure a gravitational vacuum condensate star. The condensate is not decorative language. It is the core physical claim. The interior vacuum has condensed, in the quantum mechanical sense, into a new phase. The question this raises about ordinary matter is significant. We tend to think of matter as something fundamentally distinct from the vacuum. Matter is stuff, vacuum is emptiness. Quantum field theory has known for decades that this distinction is less clear than it seems. The Higgs field, which gives elementary particles their masses, is itself a kind of condensate. The vacuum acquired a non-zero value for the Higgs field, and the particles we call massive are excitations of that condensed background. Superconductivity is a condensation of electron pairs. Ferromagnetism arises from a condensation of spin alignment in the vacuum of a magnetic material. The gravastar takes this logic to the most extreme gravitational setting imaginable and says, here too, At the threshold where space-time geometry reaches its most extreme curvature, the vacuum condenses. The same quantum mechanism that gives elementary particles their mass and makes metals superconduct operates at stellar scales, producing a gravitational superatom. This object is mathematically exact, physically motivated, internally consistent, which raises the question any scientist would ask after listening this far. Internal consistency is necessary but not sufficient. Consistency with what the mathematics already predicts is not the same as correctness. The gravastar must survive a more demanding test. Two different space-time geometries must be joined at the shell with mathematical precision that leaves no room for error. What makes that possible has been sitting in the mathematics of general relativity since 1966. When physicists construct a solution to Einstein's field equations, they are solving a set of 10 coupled partial differential equations for the geometry of spacetime. In simple settings, the solutions are clean and have been known for over a century. In more complex settings, like a region where two different geometric structures meet at a boundary, the equations become enormously demanding. One specific danger lurks at every boundary. The geometry on one side might not match the geometry on the other side in a way that is physically meaningful. This is the mathematical challenge at the heart of the gravastar. The interior is de Sitter spacetime. The exterior is Schwarzschild spacetime. These are genuinely different geometric structures, arising from different sources of energy and with different curvature properties. For the gravastar to be a valid solution to general relativity, these two geometries must join at the shell without producing physical inconsistencies. The tool that makes this possible was developed by Werner Israel in 1966. The Israel junction conditions specify, with mathematical precision, exactly what properties a thin surface must carry to act as a boundary between two different spacetime geometries. They calculate the surface energy density and surface pressure that the shell must have, given the geometries on either side, for the join to be smooth. If the required values are physical, the solution is valid. If they are not, the solution fails. For the gravastar, the junction conditions produce a specific surface energy density and a specific surface tension for the shell. These values are positive and finite. The surface energy density is a real physical quantity. The surface tension is a real physical quantity. The shell is not a mathematical abstraction, but a genuine physical surface carrying genuine physical properties. Mazur and Motola performed this calculation in their original paper. Matt Visser and David Wiltshire, researchers at universities in New Zealand, published an independent analysis in 2004 using a simplified thin shell model that made the calculation more tractable. Their results confirmed the original analysis. A gravastar satisfying the junction conditions is a stable, mathematically consistent solution to Einstein's field equations. The non-rotating and slowly rotating versions have been shown to be stable against perturbations. The structure does not collapse. It does not explode. Under the conditions specified by the junction conditions, it simply persists. It is worth being precise about what this means for the status of the gravastar as a scientific proposal. The gravastar is an exact solution to the field equations of general relativity, confirmed by multiple independent mathematical analyses to be stable. It satisfies the same standards of mathematical rigor as the Schwarzschild solution for a black hole or the Kerr solution for a rotating black hole. When physicists say that black holes are predicted by general relativity, what they mean is that the field equations have exact solutions describing objects with event horizons and singularities. General relativity also has exact solutions describing objects without event horizons and without singularities. The gravastar is one of them. The theory has been built brick by mathematical brick from established tools. Its foundations are solid. What is startling is what those foundations imply for the physical properties of the object. A black hole of stellar mass carries an entropy that would fill every data storage device ever built by humanity and still barely make a dent. A gravastar of the same mass carries something completely different. It carries nothing at all. Entropy is the physicist's way of counting how many possible arrangements an object could be in while still looking like what it looks like from the outside. A hot cup of tea has high entropy because there are an astronomical number of ways to arrange the water molecules and achieve that temperature. A perfectly ordered crystal at absolute zero has low entropy because there is essentially only one arrangement that produces that configuration. Black holes have the highest entropy of any object of comparable size in the universe. This was discovered in the early 1970s by Jacob Bekenstein, who showed that the entropy of a black hole is proportional to the area of its event horizon. Stephen Hawking refined the formula using quantum mechanics, and the result, now called the Bekenstein-Hawking entropy, is one of the most celebrated results in theoretical physics. For a black hole with the mass of our star, the entropy works out to roughly 10 to the 77th power in units of Boltzmann's constant. To give that number some scale, the number of atoms in every planet, moon, and star in the observable universe combined is roughly 10 to the 80. The information content of a stellar mass black hole approaches the total atomic count of all visible matter in the entire cosmos. A gravastar of the same mass has an entropy of exactly zero. The calculation is precise. A gravastar has two contributions to its total entropy: the outer Schwarzschild geometry, with its Schwarzschild radius that coincides with the gravastar's shell, contributes a positive entropy equal to 1/4 of the shell area divided by the Planck length squared. This is the same formula as black hole entropy and produces the same enormous positive number. The inner de Sitter geometry, with its de Sitter horizon that coincides with the same shell, contributes a negative entropy of equal magnitude. The negative entropy contribution from the de Sitter interior cancels the positive entropy contribution from the outer geometry exactly. The sum is zero. A zero entropy object has no temperature. Temperature and entropy are linked by the laws of thermodynamics. A system at zero entropy has no thermal degrees of freedom, and thermal degrees of freedom are what produce temperature. A gravastar, therefore, has zero temperature. It emits no Hawking radiation. The quantum process that generates Hawking radiation from a black hole, the virtual pair production at the horizon, does not occur here because the shell, rather than being a boundary across which one particle falls in and one escapes, is a physical surface with well-defined physical processes. The gravastar sits in permanent, silent, cold equilibrium. No radiation, no evaporation, no temperature. For as long as the laws of physics hold, it persists. Contrast this with a black hole of the same mass. That black hole is slowly evaporating, radiating away its mass as Hawking radiation over timescales far longer than the current age of the universe, but finite. Given enough time, an isolated black hole will radiate completely away. The gravastar will still be there. This thermodynamic picture resolves the information paradox in a single stroke. The paradox arose because Hawking radiation carries no information about what fell in, yet quantum mechanics requires information to be preserved. A gravastar generates no Hawking radiation. There is nothing thermal to interrogate. The information paradox does not arise because the mechanism that generates the paradox does not exist. But this resolution creates a new problem immediately, and it is a serious one. Every star that has ever collapsed began as an object with enormous entropy. A massive star in its final moments before collapse contains hot plasma, turbulent magnetic fields, a complex and richly disordered nuclear environment, the thermal motion of billions upon billions of particles in chaotic configurations. The entropy is vast. General relativity says all of that entropy falls into the black hole and contributes to the black hole's already large Bekenstein-Hawking entropy. The second law of thermodynamics is satisfied. entropy increases or stays constant, and the black hole, with its area proportional entropy, absorbs the infalling disorder without complaint. A gravastar has zero entropy. This means the zero entropy quantum condensate must somehow come into being from a collapsing star that had an enormous entropy to begin with. Between the star's last moments of collapse and the completed gravastar, something had to happen to all that disorder. It had to be radiated away. During the phase transition, as the quantum vacuum snaps from its ordinary state into the gravitational condensate, the collapsing matter must shed its entropy into the surrounding space. The transition is from a highly disordered state to the most ordered possible state. A perfect quantum condensate with a single wave function and zero entropy. The laws of thermodynamics permit this only if the released entropy goes somewhere external, somewhere outside the forming gravastar. The amount of entropy that must be shed is staggering. For a stellar mass collapse, the released entropy is comparable to, or exceeding, what a black hole of the same mass would carry. All of it must escape before the phase transition completes. Whether this is physically possible, whether the collapsing system can radiate entropy fast enough for the transition to occur in the first place, has been debated since the gravastar was first proposed. For a long time, the entropy shedding problem was the most serious vulnerability in the gravastar model. Critics pointed to it as evidence that the phase transition could not actually occur. A collapsing star implodes on a timescale of fractions of a second. Radiating an enormous entropy in that window, without violating thermodynamics or producing some other catastrophe, seemed implausible. Then, in September of 2025, a team published the first dynamical model of gravastar formation during gravitational collapse. The paper traced the evolution of the phase transition in realistic collapse conditions and found that the entropy release could occur as a burst of radiation concentrated in the final instance before the shell crystallizes. The paper did not claim to have fully resolved the problem. It was a first model, with idealized conditions and open questions about whether the same results hold for real rotating stars. But it was the first result to show that the entropy shedding process could be self-consistent within a plausible physical scenario. The gravastar's formation story now has a mechanism. Its architecture is mathematically rigorous. Its thermodynamics are extreme but internally consistent. The open question now is the one that physics always demands as its final condition. Can any of this be tested against reality? The answer is yes. And it involves one of the most spectacular predictions in all of modern astrophysics. One that was impossible to test when the gravastar was first proposed, but is now sitting at the edge of what our instruments can almost measure. It starts with the question of what sound a dead star makes. When two massive positive objects spiral together and merge, the collision is not over the moment they combine. The newly formed remnant rings, vibrating at characteristic frequencies determined by its structure, radiating that vibration outward as gravitational waves. This ring-down signal is the last thing a gravitational wave detector hears after a merger event, a dying oscillation, growing quieter with each cycle, fading into the noise over fractions of a second. Physicists call these vibrations quasi-normal modes. Each mode has a frequency at which the object rings, and a damping time over which the ringing fades. Together, the frequency and damping time form a kind of acoustic fingerprint of the object. For a black hole, the quasi-normal modes depend on exactly two things: the mass and the spin. Nothing else. The interior, the singularity, whatever is happening inside the horizon, contributes nothing to the sound. General Relativity's no-hair theorem, which states that a black hole is completely characterized by its mass, charge, and spin, ensures this. The interior is causally disconnected from the exterior. No information from inside can reach the detector. For a gravastar, the situation is different. The physical shell, sitting at the Schwarzschild radius, is part of the exterior spacetime. It can be perturbed. It vibrates. When it does, Its vibration affects the gravitational wave signal produced by the gravastar. The dark energy interior also contributes, indirectly, through the mechanical properties of the shell and the boundary conditions it imposes on how waves propagate. The result is a quasi-normal mode spectrum that is measurably different from a black hole of the same mass. In 2007, Cecilia Cirenti and Luciano Rezzola published a detailed calculation of gravastar quasi-normal modes. Their paper was titled, with admirable directness, How to Tell a Gravastar from a Black Hole. The quasi-normal mode frequencies and damping times of a gravastar differ from those of a black hole with the same mass. The differences are detectable in principle given sufficient signal quality. The quasi-normal mode test is the first observational handle on the gravastar's interior structure. Every time two compact objects merge and gravitational wave detectors record the ring-down signal, that signal carries information about whether the remnant is a black hole or something else. For the mergers detected so far, ring-down signals have been consistent with black hole quasi-normal modes. This is important to say precisely. Consistent with does not mean proven to be. It means current data cannot distinguish between the two possibilities. The ring-down test points towards something more powerful still, a signal more direct than quasi-normal modes, more unambiguous in what it would mean, something that a black hole is physically incapable of producing, but a gravastar can generate naturally. A single detection of this signal would rewrite the textbooks on the spot. Picture what happens to a gravitational wave generated near the photon sphere of a compact object. The wave propagates outward in all directions. Part of it travels toward distant detectors, eventually reaching the instruments that record it. The other part travels inward, toward the center of the object. For a black hole, the inward traveling wave crosses the event horizon and disappears. The horizon is a one-way door. Once the wave crosses it, the wave is gone from the exterior universe. Detectors record only the outward traveling portion, the main ring-down signal dying away as the remnant settles. For a gravastar, the inward traveling wave hits the physical shell. The shell is a material boundary. When a wave strikes a material boundary, part of it is absorbed, but part of it reflects. The reflected wave travels back outward from the shell, passes through the interior region, reaches the photon sphere again, and partially escapes to distant detectors as a secondary signal. The part that does not escape reflects back inward again, bounces off the shell again, and sends another partial wave outward. Each successive echo is weaker than the last, diminished by absorption at the shell and by the small fraction that escapes at the photon sphere. The result is a series of diminishing pulses arriving after the main ring-down signal, spaced at a characteristic time interval. These are gravitational wave echoes. The delay time between the main signal and the first echo is not random. It depends on how close the gravastar's surface sits to the Schwarzschild radius. For a surface very close to that threshold, the delay is long, set by a logarithm of the surface's proximity to the critical radius. For a surface sitting at 1% above the Schwarzschild radius, the delay would be on the order of milliseconds. For a surface sitting far closer, it could stretch to seconds or longer. The physical meaning of the echo signal is striking. Every echo is a gravitational wave that has bounced off the physical surface of the gravastar and made it back out. A black hole cannot produce this signal. A black hole has no surface to reflect from. Every echo arriving after a merger event would be direct evidence that something reflecting is sitting where the event horizon was supposed to be. Vitor Cardoso, Edgardo Franzin, and Paolo Pani identified and quantified this prediction in 2016, developing the detailed theoretical framework for what echo signals would look like in gravitational wave data. Their analysis showed that the echo amplitude decreases geometrically with each successive pulse. The delay time is calculable from the object's compactness, and the entire pattern is searchable in existing detector data. The challenge is that the echoes predicted for the most compact gravastars are faint, well below the sensitivity threshold for confident detection in most current observations. But they might not be completely invisible. Whether any hint of them already exists in the data that gravitational wave detectors have already collected became, in late 2016, a question 3 physicists at the Perimeter Institute decided to answer. What they found turned the field upside down. In December of 2016, 3 physicists at the Perimeter Institute for Theoretical Physics in Canada uploaded a paper that detonated a quiet explosion inside the gravitational wave community. Jahed Abedi, Hannah Daikar, and Niayesh Afshordi had gone back to the data from the first 3 gravitational wave detections ever recorded and searched for something almost nobody else had thought to look for. They were looking for echoes. We established, in the previous chapter, exactly what those echoes would be. A series of diminishing gravitational wave pulses arriving after the main merger signal, each one the signature of a wave that had bounced off a physical surface rather than disappearing through an event horizon. The Perimeter Institute team chose a specific target for where to search. Not a gravastar surface, but something even more specific. A surface sitting just above the Schwarzschild radius at the scale of the Planck length, the smallest meaningful length scale in physics. They expected, based on that assumption, that echoes would arrive at a specific delay time after each merger's ring-down signal. They found something. At roughly 3 sigma statistical significance, which is the threshold physicists use as a benchmark for calling a signal interesting rather than coincidental, the pattern they predicted appeared in the data from all 3 events. The timing matched. The repeating structure matched. The signal, faint as it was, sat precisely where the theory said it should be. The physics community did not respond with celebration. It responded with intense scrutiny, which is exactly what good scientific practice requires. Other researchers downloaded the same data and ran their own analyses. Several major critiques arrived within weeks. The sharpest came from a group that reanalyzed the same 3 events with different statistical methods and concluded the signal's significance was closer to 1.5 sigma, well within the noise floor. At 1.5 sigma, a pattern has about a 1 in 7 chance of arising from random fluctuations. That is not a signal. That is noise that happens to look interesting. The disagreement was not about the data. Both teams used the same gravitational wave recordings from the same detectors. The disagreement was about how to correctly account for the many choices made during the analysis, how to choose the echo template, how to set the search window, how to calculate the probability that any pattern of this kind would arise by chance. Every analytical choice shifted the significance estimate up or down. Abedi and his collaborators responded to the critiques, refined their method, and continued standing by the tentative nature of their finding. They were careful in their language. They said, tentative evidence. They said, consistent with echoes. They did not claim discovery. The counter-analyses were equally careful. They said, insufficient confidence. They said, consistent with noise. By early 2017, the field had arrived at an uncomfortable but honest position. The existing data contained a pattern that was either a hint at something extraordinary or a statistical artifact, and no one could tell which it was with the instruments available. What the controversy actually exposed was more important than the specific claim. It revealed that the gravitational wave data humanity had been collecting was already rich enough to contain, buried in the noise, the signatures that would distinguish a gravastar from a black hole, if only the detectors were sensitive enough to see them clearly. The question was no longer theoretical. The question was instrumental. The data existed. The search method existed. The theoretical prediction was precise enough to be tested. All that stood between the answer and the question was sensitivity. LIGO continued observing. Events accumulated. Each new detection added another ring-down signal to the archive, another opportunity to search the data for the pattern Abedi and his collaborators had first claimed to see. And the question everyone was quietly asking was, does the growing catalogue of events clarify the picture, or does it deepen the mystery? By the time the third major observational campaign by LIGO, Virgo, and CAGRA concluded its catalogue in 2023, the tally of confirmed gravitational wave events had climbed past 90. Nearly all of them came from compact object mergers, pairs of massive stellar remnants spiraling together over millions of years before combining in a fraction of a second. Each merger produced a ring-down signal that detectors captured and physicists then analyzed in detail. Every single ring-down was consistent with Kerr black hole quasi-normal modes. This is the data point most often cited. When someone questions whether black holes are real, 90 events, all matching the expected vibration signature of a rotating black hole. The no-hair theorem, the result that says a black hole is completely characterized by its mass and spin, holds with remarkable precision across every one of those events. The universe, it seems, has been cooperating with textbook expectations for a long time. But here is the subtlety that gets lost in the clean narrative of confirmation. The quasi-normal mode test probes the first fraction of a second after a plan merger, when the remnant rings down from its initial distorted shape into something more stable. During this brief window, the dominant signal comes from the object's exterior geometry, specifically from the photon sphere, the region where light and gravitational waves can orbit. Both a black hole and a maximally compact gravastar have photon spheres at the same location. Both produce quasi-normal modes at the same frequencies during this initial phase. Cirenti and Rizzola's 2007 analysis confirmed exactly this. The gravastar's initial ring-down closely mimics the black hole's. The difference appears later, after the main ring-down has faded. If the object has a reflective surface, the echoes arrive. They are quieter, delayed, geometrically diminishing. In the current catalogue, no event has produced a post-ring-down signal with enough signal-to-noise ratio for a confident echo search. The events are real. The ring-downs are real. The consistency with Kerr is real. But the window where gravastar and black hole diverge lies in the region current detectors cannot yet see clearly. The 90 events are not proof that event horizons exist. They are proof that objects compact enough to have photon spheres exist and that their ring-downs match the geometry predicted for that compactness. A gravastar at maximal compactness satisfies both conditions simultaneously. One event stands out as worth pausing on. In May of 2019, detectors recorded a merger involving compact objects in the mass range between roughly 85 and 100 solar masses. This range sits inside what astrophysicists call the pair instability supernova mass gap, a region where standard stellar evolution predicts that no black holes should form. Stars massive enough to produce remnants in this range are thought to undergo a runaway pair production process that destroys the star entirely, rather than leaving behind a compact remnant. The standard picture has no clean explanation for how a black hole of that mass could form. A paper the following year examined whether a gravastar interpretation might fit the data as well as the conventional black hole merger picture, particularly given the anomalous masses involved. The conclusion was that both scenarios remained compatible with the observed waveform, 90 events consistent with Kerr, one anomalous event with unexplained masses. No confirmed echoes. The data does not resolve the question, and every observing run adds more events to the catalogue without the sensitivity needed to close the gap. Meanwhile, the most famous image ever produced of a supposed black hole was about to face the same kind of scrutiny the gravitational wave data had survived. The photograph arrived on April 10, 2019, and within hours, it was everywhere. A glowing orange crescent of fire, asymmetric and vivid, encircling a region of absolute darkness. The image had been assembled from data collected by a planet-spanning network of radio telescopes working in concert as a single virtual instrument with the resolving power of the entire Earth. The object at its center was the compact mass at the heart of the galaxy M, 55 million light-years away, containing the mass of 6.5 billion stars. The headline attached to that image, repeated by news organizations around the world, was that humanity had taken the first photograph of a black hole. Pause on that claim. What the Event Horizon Telescope actually captured was the radio emission from heated plasma in the region around an extraordinarily massive and compact object. The bright ring visible in the image is produced by the photon sphere, the region where light and radio waves follow curved orbits before spiraling outward to observers or inward toward the center. The dark region in the middle, called the shadow, appears where light is captured rather than escaping. Both of these features, the photon sphere and the shadow, require the same underlying condition: an object compact enough that its gravitational field bends light dramatically in its vicinity. A Schwarzschild black hole satisfies this condition. So does a gravastar compact enough to lie within its own photon sphere. Both produce a photon sphere at the same geometric location. Both cast a shadow from the same region. Both would appear as a glowing ring around a dark center. The 2022 follow-up image of Sagittarius A star, the compact mass at the heart of our own Milky Way, confirmed the same story. A bright ring, a dark shadow, an object whose mass and compactness are now constrained to extraordinary precision. Everything in both images is exactly what general relativity predicts for an extremely compact, extremely massive object. What neither image confirms is the existence of an event horizon. The limitation follows directly from the exterior space-time equivalence between gravastars and black holes. If both objects produce identical gravitational effects outside the Schwarzschild radius, they produce identical optical effects as well. The lensing, the photon capture, the shadow geometry, all of it is determined by exterior curvature. Exterior curvature is the same. Researchers have examined whether the precise brightness profile of the emission ring, its exact asymmetry, or the detailed dynamics of the surrounding plasma could distinguish between the two objects. Some constraints are possible. The image is consistent with the Kerr exterior metric, which is also the exterior metric of a rotating gravastar. Papers analyzing the 2022 Sagittarius A star data found that while they could constrain some alternative models, they could not exclude horizonless compact objects at the relevant compactness. The Event Horizon Telescope showed us something extraordinary. It showed us a massive, compact object that bends light dramatically and casts a shadow across 55 million light-years. What it could not show us is what sits at the center of that shadow. The next generation of the telescope is being designed to change this. Rather than producing static images, it aims to record the dynamic behavior of matter in the near-horizon region over time. Moving structures in the accretion flow might encode information about how the geometry behaves right at the critical radius. Whether that information will be enough to settle, the question remains open. The Gravastar's disguise has held against the most powerful astronomical instrument ever built. But the disguise was never designed to hold forever. The Gravastar does not exist in isolation. It belongs to a larger conversation that has been underway in theoretical physics for decades, a systematic effort to replace the broken picture at the center of general relativity with something physically coherent. Once you understand why the Gravastar was proposed, you begin to see how many other physicists arrived at similar destinations through completely different routes. The intellectual landscape is extraordinary. String theory, the framework that attempts to unify all fundamental forces by treating particles as tiny vibrating strings of energy, produces its own answer to the black hole interior problem. It is called the fuzzball, and the idea comes from Samir Mathur at Ohio State University, developed and refined over more than 2 decades. In the fuzzball picture, what we call a black hole is actually an enormous ensemble of distinct quantum states, each one a different fuzzball. A specific fuzzball has no event horizon and no singularity. It is a tangled, extended quantum object whose specific configuration encodes the information about what fell in. The event horizon of the classical black hole is what you see when you average over all the possible microstates at once, the same way a gas of atoms looks smooth and continuous, even though it is made of discrete particles. The fuzzball is the microstate. The black hole is the statistical description. Boson stars take a different approach entirely. Rather than quantum gravity or vacuum phase transitions, they are compact objects made of a coherent bosonic field, a kind of quantum fluid sustained by the self-interaction of the field and held together by gravity. The Einstein-Klein-Gordon equations, which govern the behavior of a scalar field in curved spacetime, have stable, localized solutions. These solutions are compact, massive, and produce gravitational wave signals. A 2021 analysis found that collisions between vector boson stars could produce a waveform matching the anomalous event with masses in the pair instability gap. Then there are regular black holes, which keep the event horizon but eliminate the singularity. The original Bardeen black hole, proposed in 1968, was the first solution of this type. The interior singularity is replaced by a de Sitter core, exactly like the Gravastar interior, while the exterior retains a conventional event horizon. These objects preserve the philosophical structure of the black hole, including the information paradox, while removing the most obviously unphysical feature. More recently, Hayward black holes and various quantum-corrected regular black holes have been analyzed in detail. Wormholes round out the picture. Topological features of spacetime connecting 2 distant regions, they require exotic matter with negative energy density to remain open and traversable. The Gravastar's dark energy core is precisely this kind of exotic matter, which is why some Gravastar solutions naturally shade into wormhole geometries in the mathematics. What every single object in this catalog shares is the elimination of the singularity. Every one of them, regardless of the theoretical starting point, regardless of whether the authors began from string theory or quantum field theory or modified gravity, concluded that the place where general relativity prints an error message must be replaced with something physically meaningful. The Gravastar is part of this broad consensus, even while disagreeing about the specific mechanism. The menagerie is growing, and in the past 2 years, the Gravastar itself has expanded into a family. Theoretical physics advances in 2 ways. Sometimes, a single grand paper reframes everything at once. More often, incremental papers build on each other until the accumulated weight changes what is possible to think. For Gravastars, the past few years have brought both kinds of progress. In October of 2023, a team at the University of Jena uploaded a paper that opened an unexpected new branch of the Gravastar family tree. Daniel Jampolsky and his collaborators showed that 2 Gravastars can be nested inside each other. Not merged, not combined, but genuinely nested. One complete Gravastar structure sitting inside another complete Gravastar structure, each maintaining its own shell, its own dark energy interior, its own equilibrium. The mathematics of nested Gravastars is consistent in the same way the original solution is consistent. The Israel junction conditions can be applied successively, building each layer outward, and the solution remains valid. More surprisingly, the analysis showed that the nesting could extend to an arbitrary number of shells. A family of singularity-free compact objects emerged from the recursion, each member with the same exterior Schwarzschild geometry, each member with a different internal architecture of nested shells and dark energy regions. The family tree had been a single tree. It became a forest, Separately, the long-standing accusation that the Gravastar was a mathematical toy with no plausible formation story met its most serious challenge in September of 2025. A team published the first dynamical model of Gravastar formation during gravitational collapse, tracing the phase transition from a realistic collapsing configuration rather than from idealized static conditions. The model was not a complete solution. It used simplifying assumptions about the collapse geometry and the equation of state during the transition, but it was the first result to demonstrate that the entropy shedding problem we described in earlier chapters could be resolved within a plausible physical scenario. The released entropy could escape as a concentrated burst of radiation in the final instance before the shell crystallizes. Also, in 2024, Tatsuya Ogawa and Hiroshi Ishihara at Osaka Metropolitan University constructed what they called solitonic gravastars, gravastar-like objects arising from non-topological solitons in coupled field theory systems. A soliton is a localized, stable field configuration held together by its own self-interaction, the field theory equivalent of a persistent wave that maintains its shape. Solitonic gravastars connect the gravastar picture to particle physics field theory, giving the exotic matter of the shell a more concrete physical identity. Gravastars in modified gravity theories have been explored extensively in parallel, examining how the structure behaves in frameworks where Einstein's equations are extended or corrected. Gravastars have been analyzed in theories with massive gravitons, in theories where the gravitational action is a function of the scalar curvature rather than the curvature itself, in teleparallel gravity formulations, and in theories with non-minimal coupling between matter and geometry. In nearly every case, the gravastar structure survives, modified in detail but intact in concept. The object, proposed by two physicists in 2001, has evolved into a research program, active, expanding, and pointing in one direction, toward the instruments that could finally answer what the universe has been hiding at the centers of its galaxies. The question that has accumulated through every chapter of this story, through the singularity and the information paradox and the firewall and the Gravastars mathematics and the contested echoes and the ambiguous images, that question has always had a final form. Can we actually test this? Can we point an instrument at the universe and get an answer that settles whether event horizons exist? The answer is yes. The instruments just do not exist yet. The most significant near-term advance is a pair of ground-based gravitational wave detectors currently under design. The Einstein telescope, planned for construction in Europe in the early 2030s, is designed as a triangular underground detector, shielded from the surface vibrations that limit the current generation. It will achieve a sensitivity roughly 10 times greater than the LIGO and Virgo detectors operating today. The Cosmic Explorer, its American counterpart, aims for similar improvement through dramatically longer detector arms, stretching to 40 kilometers rather than the 4 kilometers used currently. At 10 times the sensitivity, the echo search changes character entirely. The post-ring-down signal where echoes would appear becomes accessible for a broad class of merger events. If echoes exist at the amplitudes predicted for gravastars of maximum compactness, Einstein Telescope and Cosmic Explorer will detect them in years rather than decades. If those detectors accumulate hundreds of events and find nothing in the post-ring-down window, the most compact gravastar models will be tightly constrained or ruled out. For supermassive objects, the answer will come from space. The Laser Interferometer Space Antenna, LISA, is a planned, space-based gravitational wave observatory scheduled for launch in 2034. 3 spacecraft, separated by millions of miles, will form a triangle, measuring the minute stretching and squeezing of space between them as gravitational waves pass through. LISA is sensitive to lower-frequency gravitational waves than ground-based detectors, making it ideal for observing the mergers of supermassive compact objects. When two objects like the one at the center of M87 merge, the gravitational wave signal will be detectable across the observable universe. The ring down will carry the quasi-normal mode spectrum of the remnant with extraordinary clarity. If the remnant is a gravastar, the spectrum will deviate from Kerr. If it produces echoes, LISA will record them with far higher signal-to-noise ratio than any ground-based detector can achieve. Extreme mass ratio in spirals offer a third approach. When a stellar mass compact object spirals slowly into a much more massive one over years or decades, the small object traces the space-time geometry of its host with exquisite precision. Every small deviation from the Kerr geometry leaves an imprint on the waveform. A gravastar at the center of the inspiral would imprint deviations that accumulate over thousands of orbits, making the total signal sensitive to features that a single merger's brief ringdown cannot probe. The next generation Event Horizon Telescope aims to add dynamical constraints. Rather than static images, it will observe the motion of plasma features in near-horizon regions over time, encoding information about how the geometry behaves at the critical radius. Within a generation, we will have instruments capable of answering the question this entire story has been building toward. The technology is planned. The science is clear. The prediction is precise. What we are waiting for is the detector. And while we wait, the mathematics has already pointed to where the answer lives in the deepest structure of physics. The gravastar is usually presented as a theory about astrophysical objects, about what sits at the center of a galaxy, or what forms when a massive star dies. That framing is accurate but incomplete. Underneath the astrophysics, the gravastar is a prediction about what quantum mechanics does to spacetime at the Schwarzschild radius. This distinction matters. A theory about astrophysical objects can be right or wrong depending on whether the right conditions happen to occur in nature. A prediction from quantum mechanics about space-time geometry is more fundamental. It is telling us something about the structure of the physical laws themselves. Emil Mottola's comprehensive 2023 analysis identified the specific quantum mechanism responsible for the gravastar's phase transition. The conformal anomaly, sometimes called the trace anomaly, is the quantum breaking of a classical symmetry. In classical field theory, many systems obey conformal invariance, a symmetry under rescaling of lengths and times. When quantum fields are placed in a curved space-time background, this symmetry is broken by quantum effects. The anomaly has been known since the 1970s. It generates a stress tensor, a distribution of energy and pressure in the vacuum that does not appear in the classical theory. In most settings, this anomaly is a small correction. Near a forming event horizon, where the gravitational redshift diverges, it becomes large. Mottola showed that the anomalous stress tensor near the would-be horizon generates a new effective field, which he called the conformalon, and that this field couples to the vacuum energy in a way that drives the phase transition. The conformalon mediates the conversion of the ordinary flat space vacuum into the dark energy condensate that fills the gravastar interior. This is quantum field theory in curved spacetime, producing a non-perturbative prediction. A prediction about what happens at finite coupling rather than just in the limit of weak interactions. The prediction is not an approximation. It follows from the structure of the anomaly. Loop quantum gravity, the competing approach to quantum gravity developed by Carlo Rovelli and others, arrives at related conclusions through a different path. In loop quantum gravity, the quantum geometry of spacetime itself becomes discrete at the Planck scale. A massive star collapsing into a black hole does not fall into a singularity. Instead, quantum geometry effects halt the collapse and cause the star to bounce. The resulting object, called a Planck star, would also produce echoes. The timescales are different from the gravastars, but the physical conclusion is similar. The singularity is replaced, the horizon is at least partly modified, and information survives. The gravastar also connects directly to the cosmological constant problem, the catastrophic mismatch between quantum field theory's prediction of vacuum energy density and the tiny value actually observed. Motola's framework describes the vacuum energy as a dynamical condensate whose ground state is exactly zero in flat spacetime. The large vacuum energy inside a gravastar arises only in the presence of extreme spacetime curvature. This resolves the apparent paradox. The vacuum can carry enormous energy, but only in regions where the geometry compels it. In the ordinary flat universe, the energy is zero. Every aspect of the Gravastars' physics connects outward to some of the deepest unsolved problems in theoretical physics. It is not an isolated proposal about a strange astrophysical object. It is a node in the web of unfinished physics at the foundations of our understanding of space, time, and matter. The instruments being built in the next decade will be sensitive enough to let the universe answer directly. Imagine you are approaching a gravastar in a spacecraft. For the purpose of this thought experiment, the spacecraft is indestructible, and the laws of physics apply as normal everywhere outside the gravastar's surface. Far away, there is nothing unusual. The gravitational pull you feel is identical to what you would feel approaching a black hole of the same mass. The mathematics guarantees this. You are moving through Schwarzschild spacetime, and Schwarzschild spacetime does not know whether the object generating it has a singularity or a dark energy core. It only knows the total mass. As you get closer, tidal forces grow. The gravitational gradient between the front and back of your spacecraft becomes detectable. The redshift of signals you send outward increases, and the blue shift of signals arriving from the distant universe becomes more pronounced. You are aging slightly more slowly than someone far away. None of this distinguishes a gravastar from a black hole. You approach the radius at which the Schwarzschild geometry begins to curve dramatically. The photon sphere is nearby. Light from behind you curves around the object and arrives from unexpected directions. The dark silhouette of the object grows to fill an increasing fraction of your field of view. The geometry is doing exactly what general relativity predicted. Now you reach the surface. For a black hole, nothing is here. You cross an invisible threshold with no physical sensation. The geometry tips, and from this point forward there is only one direction, inward toward the singularity. You cannot send a message out. You cannot return. You have milliseconds or hours of proper time remaining, depending on how large the black hole is. And at the end of it, the density becomes infinite and the mathematics ends. For a gravastar, something is here. A physical boundary. Matter, real matter, with real tension, carrying the maximum stiffness general relativity permits. The shell you reach sits at the same radius where the event horizon would have been. If you were patient enough and your spacecraft strong enough, you could rest on it. If you somehow passed through, you would enter the de Sitter interior. The space-time geometry changes at the boundary. Inside, repulsive vacuum energy fills all of space. The geometry is expanding in the interior reference frame. Ahead of you are no singularities, no endpoints, no places where the laws of physics terminate. Every trajectory you could follow continues without interruption. The interior is a finite pocket of de Sitter spacetime, enclosed by the shell, and de Sitter spacetime is geodesically complete. The observable universe from inside the shell would be small. The de Sitter horizon radius inside the gravastar equals the Schwarzschild radius of the exterior, which for a stellar mass gravastar is a few tens of miles. The region you can see from any given interior position is bounded by that horizon. At every location, at every moment, the equations produce finite, meaningful numbers. Behind you, the shell is a wall. Getting back out through it would require defeating the mechanical balance that holds the shell in its equilibrium position, fighting both the inward pull of the gravastar's gravity and the surface tension of the stiffest material general relativity allows. The energy cost is enormous. In practice, you are contained. What exists beyond the shell on the outside is the rest of the universe, proceeding normally, completely unaware of what is inside. observing from a distance what appears to be a perfectly ordinary black hole. This is what awaits anything that falls into the universe's most compact objects, if the Gravastar model is correct. A surface, a de Sitter interior, physics at every point, and the realization that the thing everyone thought was an abyss without a bottom has, in fact, a floor. Since the 19th century, physicists have occasionally uncovered places where their theories simply stop. The equations do their work, following the logic of the mathematics wherever it leads, and eventually they arrive at a location where the output is meaningless. Infinite pressure, infinite temperature, infinite curvature. Division by zero, dressed in the language of space-time geometry, every such location represents the same confession. The theory has reached the edge of its own domain. Beyond this point, a better theory is required. In general relativity, the singularity is that location. At the center of what we call a black hole, the equations of general relativity follow the collapse of matter to its logical conclusion and produce infinity. The theory has run off its own map. The physics has no further instructions to give. A universe that contains gravastars instead of black holes is a universe where physics has no such locations. The de Sitter interior is geodesically complete. Every path through space-time continues. Every trajectory has a next step. The laws of physics hold at every point, under every condition, without a single exception anywhere in the space-time. The breakdown that general relativity predicts at black hole singularities does not occur because the singularity does not form. What does this mean for the Penrose singularity theorems? The rigorous mathematical proof we traced in the early chapters of this story. The proof that under the rules of general relativity, singularities are mathematically mandatory. The theorems do not disappear. They remain correct within their domain. What the Gravastar reveals is that the domain of the Penrose theorems is the domain of classical general relativity, the theory that does not account for what quantum mechanics does to the vacuum under extreme gravitational conditions. Add the quantum behavior of the vacuum, specifically the phase transition triggered by the conformal anomaly as the horizon forms, and the energy conditions that the Penrose theorems require are violated at precisely the critical radius. The theorems assumed that matter behaves well under extreme conditions. The quantum vacuum does not. The loophole is real, and it opens exactly when and where it needs to. This reframing has a profound consequence for theoretical physics beyond the specific case of gravastars. It suggests that the singularities predicted by general relativity are mathematical artifacts of a theory used outside its domain of validity, the same way the ultraviolet catastrophe in 19th century radiation physics produced an infinite prediction from a theory that needed quantum mechanics to correct it. Just as quantum mechanics replaced the infinite prediction of classical radiation with Planck's finite spectrum, quantum field theory in curved space-time may replace the infinite prediction of the classical singularity with the Gravastar's finite de Sitter core. If this picture is correct, the universe does not contain any places where physics fails. Every region of space-time, no matter how extreme, is governed by laws that remain coherent and complete. The map has no edges. There are no territories beyond physics. That would be one of the most significant discoveries in the history of science. Not a new particle, not a new force, but the confirmation that the laws of nature have no exceptions anywhere in the universe. The implications do not stop there. For 50 years, the smartest people in theoretical physics have been wrestling with a problem that sits at the intersection of quantum mechanics and general relativity. The information paradox, the contradiction that arises when Hawking radiation destroys the quantum mechanical record of everything that ever fell into a black hole. The attempts to solve it fill entire libraries. Complementarity, the idea that an infalling observer and a distant observer see different but self-consistent realities, and information escapes as the Hawking radiation without either observer experiencing a contradiction. firewalls, the idea that the horizon is surrounded by a high-energy wall of radiation that incinerates in falling observers but preserves quantum unitarity for outside ones. Fuzzballs. The string theory microstate picture, where every black hole is secretly a specific quantum configuration that stores its own history. Island formulas. A recent technique from quantum gravity where the entropy calculation is modified by including contributions from disconnected regions of spacetime far inside the black hole. Each of these proposals is brilliant. Each is motivated by a genuine insight. Each is also extraordinarily complex, requiring new physics, new conceptual frameworks, or both, and each creates new puzzles even as it resolves old ones. The Gravastars resolution is different in character. It does not add new machinery to handle the information paradox. It removes the condition that generates the paradox in the first place. The information paradox arises because of the event horizon. The horizon divides the universe into two regions with different causal access. Information inside the horizon cannot reach the outside. Hawking radiation, generated at the horizon, carries the energy but not the information of what fell in. When the black hole eventually evaporates, the information appears to be lost. Remove the event horizon, and none of this follows. With no event horizon, there is no region from which information cannot escape in principle. Quantum unitarity holds everywhere and at all times. The universe keeps a complete record of its own history. The information in a gravastar is stored in the dynamics of the physical shell and the structure of the dark energy interior, both of which are governed by physics that preserves information in the standard quantum mechanical way. The gravastar does not need a clever new mechanism to save unitarity. Unitarity was never in danger in the first place. Consider what this means against the backdrop of where we have traveled. The singularity problem. Resolved because the de Sitter interior replaces the singularity with a geometrically complete space-time. The information paradox. Resolved because there is no horizon to trap information. The firewall paradox. Dissolved because no horizon means no horizon-related quantum drama. The cosmological constant problem. Connected through Matola's framework to the same mechanism that produces the gravastar interior. 4 of the deepest unresolved problems in modern physics. The gravastar does not solve all of them definitively because it remains a theoretical proposal awaiting observational confirmation. But it connects them. It places them under a single explanatory roof. It shows that they may all be symptoms of the same underlying assumption, that the classical picture of gravitational collapse is complete. If the gravastar is correct, the assumption was wrong, and the universe's most famous monster was never a monster at all. Go back to the beginning. Before the quasi-normal modes and the entropy calculations and the nested shells, before the firewall paradox and the conformal anomaly, before the gravitational wave detectors and the planet-spanning radio telescope arrays, go back to the image. The ring of white-hot fire curving around a perfect, absolute darkness. Light bending and swallowing itself at the edge, the void at the center. The most famous monster in the universe, staring back from every magazine cover and classroom wall. We started this story by saying, you think you know what it is. We started by telling you there were cracks in the foundation, a singularity the theory admits it cannot describe. A paradox about information that has occupied the sharpest physicists for half a century, a firewall that should incinerate anything crossing the boundary. We told you a picture that feels settled and confirmed is built on something that does not fully hold together. What if the void at the center of that image is not a void? What if the absolute darkness is not a region beyond physics but a region of different physics? A pocket of de Sitter space-time where the same vacuum energy driving the expansion of the entire universe pushes back against gravity and wins? What if the boundary of that darkness is not an invisible mathematical line but a physical surface, a shell of ultra-stiff matter at the maximum stiffness relativity allows, holding the line between two radically different space-time geometries. What if the monster has a face? Powell, Mazur, and Emil Mottola proposed this in 2001, and the community moved on. The mathematics has been checked. The stability has been confirmed. The thermodynamics have been worked out, producing zero entropy and zero temperature and no Hawking radiation. The quasi-normal modes have been calculated and shown to differ from a black hole's. The echoes have been predicted and searched for, tentatively, inconclusively. The next generation of detectors is being built to do the search properly. The object at the center of M87, the one whose photograph changed scientific history, has a mass equal to 6.5 billion of our stars compressed into a region roughly the size of our solar system. Its gravity bends the light of everything nearby into a glowing ring visible from 55 million light-years away. Its influence shapes the entire galaxy surrounding it. By every measure that existing instruments can apply, it is consistent with a black hole. By every measure that existing instruments can apply, it is also consistent with a gravastar. In the early chapters of this story, we talked about carrying a broken engine in a car that looks perfect from the outside. The singularity has been sitting in the center of general relativity like that broken engine since 1916. Physics has been driving carefully around it for a century, treating it as someone else's problem, waiting for the complete theory of quantum gravity to arrive and clean up the mess. The gravastar is the proposal that the mess can be cleaned up now, with the quantum mechanics we already have, applied to the curved space-time we already understand, producing a phase transition we can calculate and predict and test. The universe may be telling us that it contains no broken places, no edges to the map, no regions where the laws of physics throw up their hands and stop, only objects stranger than we imagined. Governed by physics we are only now beginning to read. The most feared object in the cosmos might turn out to be the most perfectly physical thing in existence. Strange beyond imagination, describable with equations, testable with instruments, ultimately knowable. The monster, at the end of the story, has a face, and we are building the instruments to see it.